Hi everyone. Let's just put this one. Okay. So basically, the first item is the actual growing demand in bandwidth. We see that in data center, and not only in data center only, even if in both in telecommunication and both in a data center. Currently, today is a lot of deployment of 400G, and currently already began with 800G going towards 1.6, etc., etc. So the idea is to have the smallest form factor, the fastest module, and the lowest with the power consumption and with the best performance. Basically, on MASSTART, we were targeting the silicon photonic market, which, as you can see on this slide, is actually growing and growing. The blue portion is the increase of the portion of the silicon photonics. So basically, the trend, if you go down the road in the coming 2 years, will be a lot of silicon photonics. Of course, it's come with the price. The price of this technology is, I think this described it the best, and that the assembly and all of the surrounding for the laser and connectors are a huge portion of this cost of the transceiver. So it's one thing to build up the prototypes. It's a completely different stage to transfer it into mass production. Down the road, we see what we are doing in that manner, both in MASSTART and both in other transceiver developments, in order to ensure like a good yield and a cost-effective module per performance. So basically, if you can see on this flow chart, these days we are running most of the optics at 100G, and this is exactly what we're doing also in MASSTART. So most of the electrical ports are derived by 100G services, and for the actual one that we're doing, we have in MASSTART 3 prototypes, 3 demonstrators for 400, 800, and 1.6 terabit. So you can see down the road how it grows rapidly, and you will see another one down the road that shows the transformation between the common pluggables, I mean like this, the commercial form factors like QSFP-DD or OSFP based, and then you'll see how it transfers into onboard optics, and then the target is to reach into a full core packaging that will actually replace the entire form factors and pluggables. So this is something that is specifically for Tolga, but currently the trend, it's not appearing here. It's to explore in the regime of 200G per lane. So this is something that I think will be the next step. As described, today's approach is actually going with pluggables for 400 and 800G. In the mid-future, it's transferring to onboard optics. When I'm writing in far future, it's like in, let's say, 2 years, let's say to have it completely stabilized around 3 years to go into core packaging. However, after saying all of that, the transform from pluggables into onboard into core package optics, even with 200G electrical lanes, 200G rates per lane, we will still have transceivers coexist. So this one here on the left button will not disappear. But I think at the end of the day, if we're going to have those ones, and those are what we are targeting also in MASSTART, transferring from the pluggable into some kind of an open platform that resembles some kind, it's not a co-packaged, but it's the way to go there, then it will be much more cost effective than using the regular pluggables. So basically in MASSTART, we had a couple of demonstrator, and the first one was a 400G DR4 transceiver. Basically, it's based on a commercial DSP, while we used a TOSA that populated on the peak using a driver and TIAs from commercial companies. And we had the ROSA. So this will be the time to give some acknowledgements. Those are chips that were done in Bright Photonics, that also are in Dust Photonics. And this is the actual peak done with Leti and all the partners of MASSTART. So basically, this is the first prototype for the 400G OSFP model. Again, you can see the form factor, the actual, all the fiber connectivity into the MPO, and the final one. This is in the making. We are not there yet, but we are very close. And here comes the road to how to actually take this one and transform it into a mass production. So it all began with the basic simulations and not so basic. Those simulations are a complete mapping of a frequency and time domain for all the traces that we're using, both on the host side and both on the line side. Those shows the actual result up to 53 gigabaud PAM4, and of course it goes way behind it. It's tackling everything that goes with insertion loss, return loss, TDR, etc. Once this is established, we actually manufactured and designed those coupons that at the end of the day were relying on the simulations that we approached. And by the way, this was also co-work with IZM, with Bogdan and Tolga. And at the end of the day, we had basically simulated specific signals on the time domain, and we got almost a replica, a very, very close replica under lab testing. So this was the first benchmark from our side to begin, and from any vendor that is doing transceiver. So we are like designing on the manufacturing stage into the SMT, and then getting the actual devices itself. At the end of the day, this is an open platform to demonstrate the entire electrical domain on several configurations on either Rosenberger, whoever familiar with those RF connectors, or Ardent. So those give us the entire work on the electrical domain to better see what performance do we actually have. Here you can see the actual test result on the master demonstrator. So on this is one of the master demonstrator. Of course, we investigated a couple of PCB high-end materials in order to achieve those results. Those, of course, the electrical domain that goes into the driver, and from there into the TOSA and the optical domain. There is also, of course, we invested a lot in mechanical jigs for actually having also an optical demonstrator before this is going into the form factor. Once it's into the form factor, and if you have some issues, then you are in a lot of problems trying to stabilize those modules into a mass production and an actual ability to have, let's say, a replica of what you are achieving in terms of calibration and testing for each and every module. The number 2 prototype in terms of MASSTART actually takes the newest DSP in the market, which has going like 8 lanes, both from the host and the line side of 53 gigabaud. This is again Bright Photonics chips with some commercial chips that we are using from a third vendor. And it was designed in a manner that each one of those, both prototype 1, 2, and 3, which is like the stage for an open platform of 1.6 tera, will be in a manner that you, at the end of the day, will be able to replicate and to have more than a couple of samples. The idea is to have something robust. This is why there is a lot of interest in the thermal design, in the signal integrity simulations to have the best margins for the link budgets to come, etc. Even the connectivity and everything that we are connecting from the fiber outside, and of course the form factor that has its own limitation. So the idea at the end of the day is to have like a flow, a real flow. This is something that we did also with the colleagues on MASSTART, with FICONTEC and all the other partners, that actually building a procedure to taking this kind of models and going through like a real work instruction that builds from the TX flow throughout every stage for the inspection and stuff, and the population of the TOSA peak and the alignment, etc., wire bonding, etc., both on the TX, both on the RX. The idea that if this work instruction along with the restrict design considerations is done properly, then we can easily take those MASSTART and move it to the next stage. Other than several prototypes, the idea is to have a high yield on the models itself. This, of course, will reduce the cost of the models itself. And of course, each one of the prototypes embeds within a different kind of DSP. Some of them are very, very new in the market, but the idea is to have the envelope of the entire form factor module or the open platform to have everything ready in terms of ISI, thermal, design, power, everything. And then it's easy, and I think this is the way it's going now on MASSTART in terms of taking those prototypes and merge them into the next level to have a better replica for each one of the demonstrators that were shown here. Basically, if I'll need to conclude, so the silicon photonics obviously becoming for the SR on the data center, they will be the short reach, the low cost transceiver. So what from our side must be done is the actual ways to reduce the packaging cost and the assembly procedure. And this is why it has to build in that manner. Basically, those demonstrators currently will run from the 400G pluggable transceiver into the 800G, the onboard optics, and into the platform, the 1.6 tera, that will evolve eventually on a co-packaging. I think that's it. I think this is on time.
Thank you very much, Boaz. Are there any questions from the chat? We have time for one very short question. If not, I would ask you for a very short opinion on co-package optics.
Yeah, go ahead.
Yeah, what do you think? Will it happen soon with the concepts we've seen so
yes.
far?
Yes.
Okay.
For sure. Much more than, let's say I said in the far future, like 2-3 years. So we strongly believe that I think in the next 18 months, give or take, you will see first one.
Interesting. Thank you very much.